Welcome back to the wonderful world of physics. This is the beginning of chapter 24 on electric current, and section 1 is also titled Electric Current. So in this chapter, we're going to learn all about electric currents, and that will set us up for chapter 25, which will be about electric circuits. We've been looking so far at electrostatics, meaning the interaction between charges when they are standing still. And we're now going to bring the discussion into electrodynamics, which means when charges are moving. With electric current, we define current as the net rate of charge crossing an area. So there is the equation: current is the charge that's passing through a given, let's say passing by a given point, divided by how much time it took to pass by. And this is for if there's a steady current. The units you can see in that equation, it's coulombs per second, but we define the ampere, named after the physicist André-Marie Ampere. We define that as a coulomb per second. Very often, especially in industrial applications, you'll hear this called an amp. So it's an amp or an ampere. Now, if it is a time varying current, we'll not just say delta Q over delta T, but rather it becomes a derivative, dQ over dt. The current is the direction of positive charge flow. Now, this is very important to understand, because remember, usually when we're talking about electric current, we're referring to the flow of electrons, which are negative charges. So if you look at these diagrams down below, if we had a bunch of protons, or they could be positrons, but positively charged particles, moving to the right, that is positive charges moving to the right, so we say the net current is to the right, because current will always be defined as the direction of positive charge flow. But then imagine we have electrons that are moving to the right. So that is negative charges moving to the right. We say that current is going to the left. And it's kind of weird when you first hear it, because you're thinking the things that are actually flowing are going to the right. Yet since they are negative, we're going to say that the positive flow is to the left. Now, let's say we have a mixture of pluses and minuses. So here we have this particle, this ion maybe, whatever it is, but it's got two positives and a minus. Well, you can think of the net charge of that is one positive, because it's +1 + 1 - 1. So overall, it's a +1, and we'll treat it like the proton in the picture up above. If it's moving to the right, the net current is going to the right. If we think about a neutral object, like maybe a neutron, it's not moving, or it is moving, but there's no current because you have no movement of charge. In the section, there's a got it question. It says, which of the following represents a non-zero current? What's its direction? So the first one, it says a beam of electrons moves from left to right. And so there you see I've drawn a picture of a beam of electrons moving from left to right. And we think, what exactly is going on there with current? Well, remember that if negatives are going to the right, we're going to envision that as positive charge going to the left. So we'll say current is to the left. Question B, a beam of protons moves upward. All right, so there I've drawn a bunch of positive charges because protons are positive going upward. And then we say, okay, since the positives are moving upward, that is the direction of positive charge flow. So we'll say that the current is upward. Question C, it says in a solution, positive ions move left and negative ions move right. There I've drawn a picture, positive ions moving left, negatives moving right. Let's think about these individually. If the positives are moving to the left, then they've got a leftward current. If the negatives are moving to the right, then they've also got a leftward positive current. So in both of those cases, there is a leftward current. Question D says blood carrying positive and negative ions at the same speed moves up through a vein. Well, in that case, positives are going up, negatives are going up. The negatives going up makes for a downward current, so overall it balances out. And so we have zero current. And then E is a metal car with no net charge speeds westward. And so if there's no net charge, it's like a neutron. It's one neutral body. And so there's no movement of charge, so there's zero current. Let's now zoom in to a wire and look at a microscopic look at current. In a conductor, and we can think, for example, a wire, charges have random high-speed motion. Random means there's no direction preference. And so there's not automatically a current. You've got some negatives moving to the left, some going up, some going down. And if there's no preference of all these billions of charges moving around randomly, if there's no preference to going left, right, up, or down, it will all balance out, it'll all zero out. So there is no current. But when there is a current, there's a small drift velocity. And so here we have a wire, and there's a current going through it. The wire has a cross-sectional area of A, and let's just take this length, the segment of the wire, length L. And you've got all these positive charges, they can represent nuclei of atoms, and the electrons will drift slowly to the right. And we'll talk as we develop this chapter why they're drifting to the right. And we can say that if we define lowercase n as how many charges per unit volume, then let's multiply n by the volume, and we get n times area times length. Okay, so that's the geometry of the volume there, and that's the total number of charges. So the total charge, that was NaL, was the number of charged particles. Now the actual charge in coulombs is going to be that NaL times whatever the charge on each particle is. If we're talking about electrons, then the elementary charge. And then let's bring into this what is the time aspect, because we're going to relate charge and time to be the current. The time aspect is the length that they travel divided by whatever speed they're traveling to pass a given point. And so when we put all that together, the current, we can say, is the total charge that passes a given point in that given time, so NaL times Q, divided by however much time it took for that charge to pass, L over, I'm going to call this V sub D. I should have mentioned this in the line up above. V sub D stands for drift velocity. I had that written at the top of the wire up here. And in the end, the current is the number of charges per volume times the cross-sectional area times the charge times the drift velocity. So as we think about that, the current, what's it based on? How many particles there are, how big an area they get to pass through, the charge on each one, and how fast they're going. There's the equation again. Current is N times A times Q times V sub D. Let's look in the book at example 24.1. It says a 5 amp current flows in a copper wire with cross-sectional area 1 square millimeter, carried by electrons with number density 1.1 times 10 to the 29th electrons per cubic meter. Find the electron's drift speed. We're going to get a surprising result here when we do this. You can see I've listed out all the given information. Be careful with units of area. 1 square millimeter is 10 to the negative 6 meters squared, and is 1.1 times 10 to the 29 per cubic meter. And of course, there's the charge on an electron. When we plug all that in, we get 0.28 millimeters per second. Now think about how slow that is. Just envision a millimeter. that the current travels through a wire, and this is a typical speed, less than a millimeter per second, which sounds kind of weird because you think when I turn on the lights, I'm not waiting that long for the current to go through, but it's kind of like when you have a garden hose, and if it's been used any bit, then it already has water in it. And you turn on the spigot, and you're not waiting for the water to go from the spigot all the way through the length of the hose and then to come out the other end. If there's already water in the hose, then all that happens is you turn on the spigot and there's pressure immediately against the water in the hose that's near the spigot. So it immediately pushes the water out the other end. It's only when you first hook up a garden hose where there's no water in it that you have to wait for the water to go through. But with electrons in a conducting medium, the electrons are already in it. They just need that little bit of pressure. Let's talk now about current density. Current can also travel through fluid or between or through cell walls and organs. The magnitude of current can vary. I'm going to introduce a new quantity here, current density, and we're going to use the uppercase letter J for that. Notice it's a vector, and it refers to current per unit area. So we're going to imagine that just like the capital A of the previous example when we were looking at a wire, there's a cross-sectional area that the current is going through. So the current density is current per unit area. Now, if we take that previous equation, what I've written here in black, I equals NA times Q times drift velocity, divide by area. On the right-hand side of the equation, the A's divide out, and we're left with current density, vector, is the number of charged particles times the charge on each times the drift velocity. In the book, at the end of section 24.1, it says when the current density is uniform, as in a wire, the total current is just the product of current density and the wire's cross-sectional area. But when the current density varies, it's necessary to integrate to find the total current. See problem 57. So let's look at problem number 57 together. You can see my drawing there, similar to the one in the book. It says a metal bar has rectangular cross-section 5 centimeters by 10 centimeters. The bar has a non-uniform conductivity, and as a result, the current density increases linearly from 0 at the bottom to 0.1 amperes per centimeter squared at the top. Find the total current in the bar. All right, we're going to start using this equation that J, the current density, is I over A, and we want to find the current, so that means current is J times A. Let's look at the picture as I've drawn it. 10 centimeters is the height, 5 centimeters is the width. I've made X go in the direction of the height, so up, and the Z direction is the direction of current. So what we're going to do is use this equation, I equals J times A, but we can't simply multiply those because J is changing. But what we can do is take these little strips of width dx and length 5 centimeters. And they're so infinitesimally short that we can consider current being constant through each of these rectangles. And then we're going to take each of these rectangles and then add them all up. So each of these rectangular strips has an area dA, which is 5 centimeters times dx. And therefore we can say that as a vector, dA is the area times the direction then current is flowing. And we're going to have current flowing in the Z direction, so the k-hat direction. So we have dA is 5 centimeters, which is the width, times dx, k-hat direction. Our equation, I equals J times A, becomes an integral because we're going to add every J times little tiny area dA and then add all of those, all of the currents of all those rectangular strips. So we have the integral of J dotted with dA. So we can say it's the integral of J dA because J dotted with dA, those vectors are in the same direction, so it's just JdA. And now we go down to this line, and we're going to make substitutions. So first we need the limits of integration. I don't want to integrate over dA, but rather dx. So we're going to be integrating up the height of the bar, so from 0 to 10 centimeters. J, now it said that the current density changes. It goes linearly from 0 to 0.1 amperes per centimeter squared. How that would go as a linear equation would be 0.010 times x. And you can see that, so the limits of it are if x is 0 at the bottom of the bar, that would indeed give 0. If x is 10 centimeters at the top of the bar, that would give the maximum 0.10 amperes per centimeter squared. So you can see that J needs to be 0.01 amperes per centimeter squared times x. Then what about dA? Well, the area of every one of those rectangular strips is the width 5 centimeters times dx. So here we have the full integration, or the full integral. Let's factor any constants out to the side. We have 0.010 and 5 centimeters. And so that's going to leave us with 0.50. And then what's left on the inside is the limits of is the integration of, we have x and dx with those limits of integration from 0 to 10 centimeters. So then we integrate, x dx becomes 1/2 x squared, and here I've moved the 1/2 out to the side, making it 0.025, and we have x squared, and we're doing that from 0 to 10 centimeters, and when you plug all that in, you get a current of 2.5 amperes. Let's now look at example 24.2 at the end of the section. It says through the cell membrane. So example 24.2 says, ion channels are narrow pores that allow ions to pass through cell membranes. A particular channel has a circular cross-section 0.15 nanometers in radius. It opens for 1 millisecond and passes 1.1 times 10 to the fourth singly ionized potassium ions. Find both the current and the current density in the channel. All right, so it says that each channel has a radius of 0.15 nanometers. Here I've done that in meters. The area is pi r squared. And it says it's open for 10 to the negative 3 seconds. We can say that the total charge that flows, since in that time it says 1.1 times 10 to the fourth singly ionized potassium ions, that means 1.1 times 10 to the fourth of these ions that each have a charge of positive E. Calculate the current and current density. Let's first calculate current. It's the charge that passes through over the time. So there is the number of charged particles times the charge on each one, divide by the time, and we get 1.8 picoamperes. Next question is, what is the charge density? So we take the answer that we got in part A, and here's the non-rounded answer, 1.762 times 10 to the negative 12 amperes, divide by the cross-sectional area, and we get 2.5 times 10 to the 7th amperes per meter squared. And by the way, 25 megaamperes per meter squared is about 4 times the maximum safe current density in a typical household wiring. That is the end of section 24.1. Have a great day.